Okay, welcome back everyone to session 2 of our virtual AAG sessions on urban and spatial networks. We've got 4 papers coming up in this session, followed by a live Q&A session. So I'm going to get the session kicked off with a presentation on extracting the backbone of interlocking city networks. I'm Zachary Neal. I'm coming from Michigan State University. And this is a joint project along with Rachel Domagalski and Bruce Sagan, who are both in the mathematics department at Michigan State. So the first thing we can review is what is an interlocking city network. So this is a type of city network that many of you will be familiar with because it was popularized by the Globalization and World Cities, or GAWC, research group, in particular by Peter Taylor, as a promising way to measure world city networks. So the interlocking city network approach begins with a bipartite matrix of firm office locations in cities. So in this very simple example, we have 3 cities, Amsterdam, New York, and Perth, and 3 firms. So for example, firm A has a location in Amsterdam, a location in Amsterdam only. Firm B has locations in all 3 cities, and firm C has a location in Amsterdam and New York only. So we can transform this type of data, which is very easy to collect, into a co-location data set by way of bipartite projection. And this gives us an adjacency matrix. So for instance, what we see here is that 2 firms maintain an office in both New York and Amsterdam. The conceptual argument that Taylor offers is that these offices interact to coordinate the firm's work, and that therefore these inter-firm coordination ties forge a network, a link between Amsterdam and New York. So through the talk, I'm going to be using as an example some of the Globalization and World Cities data collected in 2016. So this data takes that type of form as a bipartite matrix, but it's much larger. It includes 707 cities around the world and 175 firms. And so this data represents the location of each of those 175 firms in 707 cities in 2006. So using the typical interlocking city network approach, we get a network that looks something like this. And one of the important features of the interlocking city network approach is that the links in these networks are valued. They have a strength. So in this particular case, the strength of the New York City-Amsterdam link is 22. That is, there are 22 firms that operate office locations in both places. But this, of course, raises an important question. Is 22 a lot? Is it enough to be statistically significant? Do we care about links that are 22 as opposed to, say, 25 or 300? And what I'd like to focus on in this talk is the fact that ignoring these sorts of questions and simply treating all links of any value as significant can be problematic because it winds up giving us a very dense network focused on just the biggest cities, something like we see here on this slide. So we can resolve this problem by thinking about network backbones. So as I mentioned, each link in an interlocking city network has a weight. In this example, the weight of the New York City-Amsterdam link is 22. The backbone of this network contains only the statistically significant edges. So we can think about what this might look like in the traditional interlocking city network and a backbone network. In the weighted interlocking city network, we'll see a network that focuses just on the biggest cities. A backbone network can be helpful in this case because it allows us to focus on just the statistically significant links in this network, just the most meaningful intercity links, and therefore not just the biggest cities, but the cities that are participating in meaningful intercity interactions. So the challenge then is to find a way to locate these network backbones, to extract the network backbone from an interlocking city network. And so in this presentation, I'll be using a new R package called Backbone. So you'll see a couple lines of code here that allow us to use the package. So we can install the Backbone package using the install.packages command. We can load it using the library command. And the package has a number of helpful documentation files. So the code !backbone will let us read the documentation, describe how all the commands work. And the command vignette backbone will allow us to read a very detailed example and an example data set so that we can start to understand how this package works. So for the rest of the presentation, I'm going to give some examples of the types of backbones this package allows us to extract. So just one note on installing the package, we've made version 1.1 available now, but very soon version 1.2 will be available that runs much, much faster and has a number of other advantageous features. So as the Backbone package works, the Backbone extraction options come in 3 flavors. So all of them work in a very similar way. So we start with our weighted interlocking city network. We then extract a backbone null model. There are 3 different ones, and each of these give us 3 different versions, 3 different perspectives on the backbone of the interlocking city network. So the 3 I'll talk about today are the hypergeometric backbone, the FDSM, or fixed degree sequence model backbone, and the SDSM, or stochastic degree sequence model backbone. So we can think first about the hypergeometric backbone. So the command to extract a hypergeometric backbone is really quite simple. The command is hyperg, and in this case, data is simply our original bipartite data. Remember the locations of firms in cities arranged as a matrix. So running this command is really quite fast. It takes about a half second. So the hypergeometric backbone adopts a specific view of what it takes to make an edge, a tie in this network, statistically significant. It compares the number of observed shared firms to what we would expect if cities maintained their sizes, but firms were allowed to locate randomly. So we can return to our New York-Amsterdam example and see what that might look like. So as we know, we observed 22 firms to maintain offices in both New York and Amsterdam. And we want to answer the question, is 22 a lot? Is it significant? If we adopt the hypergeometric backbone, we get this sort of distribution of the number of offices we would have expected them to share under random conditions. And we can see there's a bit of a range, but under random conditions, we would have expected New York and Amsterdam to only have shared about 16 firms. So this tells us that the fact we see them share 22 firms is actually quite large compared to this random case. And we would conclude under the hypergeometric backbone that the New York-Amsterdam link is significant. So once we've extracted our hypergeometric backbone, we can extract the network. And that requires a second command, the extract.backbone command. So we feed this command our hypergeometric backbone and a specific alpha level. So in this case, we're going to keep all of the city pairs, all of the edges that are statistically significant at the 0.05 level. And we get a network that looks something like this. So rather than contain all 707 cities in the original data, this backbone focuses on a much smaller subset of the 314 key cities that participate in one or more statistically significant link. So we can see the network is still fairly dense, but we can start to observe some of the subgroups. They become visible in the periphery. So we start to see a bit more nuance in this hypergeometric backbone network. So the next version of backbone we might want to extract provides us a slightly different perspective, the FDSM backbone, or fixed degree sequence model. So again, the code to extract this type of backbone is quite simple. It's FDSM, and then in parentheses data, our original data. Now, this type of backbone is quite a bit more complicated to extract. It takes quite a bit more time. On my machine, about 30 minutes. So this adopts a much more constrained view of what it might take for 2 cities to have a statistically significant link. It compares the observed number of shared firms to what we would expect if both cities and firms maintained their sizes, but firms were locating randomly. So again, we can compare the New York-Amsterdam case. We know they share 22 offices, but under this much more restricted version of a backbone, we see a slightly different distribution of the number of offices we would have expected them to share, even under random conditions. So we observe they share 22, and even under random conditions, we would expect that's about the number they ought to share. And so we would conclude in this case, the New York-Amsterdam link, although it's 22 in strength, is not statistically significant. It's not particularly surprising given other characteristics of the data. So once we've extracted our FDSM backbone, we can obtain the network. And that's what I've done here. Again, retaining only those intercity links that are statistically significant at the alpha 0.05 level. So here we can see this network zooms in a bit more closely because it's using a more stringent conception of the backbone, now focusing on just 189 key cities that participate in this more restricted view of what counts as statistically significant. So at this level, the network becomes much less dense. The core is still clear, but we can also start to see cities playing bridging roles into these peripheral subgroups. So it provides a still more nuanced view of this world city network. So the final type of backbone that the package currently makes available is the SDSM, or Stochastic Degree Sequence Model Backbone. So once again, the command to extract the SDSM backbone, very simple. The command is SDSM, and in parentheses, our data set. And this is quite a bit faster than the FDSM backbone. It takes only about a minute. And this represents a sort of middle ground between the very liberal assumptions of the hypergeometric and the very stringent assumptions of the FDSM backbones. So this version compares the observed number of shared firms to what we would expect if cities and firms roughly maintained their sizes. So not exactly under the FDSM, but only roughly maintained their sizes. But again, firms chose their locations randomly. So returning to New York and Amsterdam, we know they share 22 offices. The SDSM backbone says 22 is about what we would expect, even if firms chose their locations randomly. And so again, we would conclude the New York-Amsterdam link is not statistically significant. So from there, we can extract our network backbone at the alpha of 0.05 level. And we see here the most focused version of the world city network, in this case focusing on only the 112 cities that meet this very restrictive conception of what it takes for an intercity link to be statistically significant. So again, the bridges to the periphery are clear, but now the density has fallen to such a level that we can even start to see the structure of the core of this world city network, which in the earlier versions of the backbones was obscured. So at this point, you might ask, well, we have three flavors of backbone. Which flavor is right? Which backbone is the right backbone? And that's a difficult question because there is no right backbone. Each of these backbone techniques comes with different assumptions and provides a slightly different perspective on a world city network. But there are some important differences. So the hypergeometric backbone is very fast, about a half second, but it offers a fairly liberal test. It includes lots of edges, and so that's going to yield much denser backbones, much denser world city networks. It's also going to yield networks that are quite different from both the FDSM and SDSM backbones. So a hypergeometric backbone tends to be correlated with the other two at only about a 0.2 level. So quite a different backbone because it's such a liberal test. The FDSM backbone, we can think of this as sort of the opposite end of the spectrum, is really very slow. It takes about 30 minutes now. It's a very conservative, very stringent test and yields much sparser backbones. But it yields backbones that are really quite similar to the backbones we get using the SDSM method. SDSM and FDSM backbones are often correlated about 0.8 or higher. And finally, the SDSM, we can think of this as a bit of a middle ground between hypergeometric and FDSM. It's quite quick, taking only about a minute to compute. It offers what I'd like to think of as more relaxed, more reasonable assumptions that don't assume firms and cities maintain their sizes, but roughly maintain their sizes. It allows a bit of variation in the number of firms located in each city and the number of cities located by each firm. It yields the sparsest backbones, and as I mentioned, is often yields backbones that are quite similar to FDSM with a correlation of about 0.8. So in practical terms, what do you do if you're interested in looking at interlocking city networks? So if you're interested in using an interlocking city network, I think it requires asking what you want the edges to mean. If you want the edges to simply capture the number of shared firms, then using a regular interlocking city network is perfectly acceptable. A backbone is not necessary. However, if you want to interpret your interlocking city network as telling you something about where significant economic links occur between cities, then using a backbone can be helpful. And there are a couple guidance points for selecting among these. So if you have a really, really big network, say many thousands of cities, many thousands of firms, the hypergeometric backbone, although it's a relatively liberal test, is the only one that's really going to be practical at this point. If you have a more modest network, the FDSM will work. It'll be a bit slower, but certainly available. And if you have a more modestly sized network, but you'd like a very stringent test, something that really zooms in and allows you to see not only the periphery, but also the structure in the core, then the SDSM may be a good option. So I think I'll stop there. I'll take a look at the chat to see if any questions have come in. But I do want to say thanks to the rest of the research team. This work has been supported by a grant from the NSF. So thanks to Bruce Sagan and Rachel Domagalski, both my colleagues in MSU Math. If you're looking for more information about this, we maintain a website at zacharyneal.com/backbone. You can also learn about the Backbone package on the CRAN archive, and I'm always available to take questions by email.